Not know what is going on.
Yeah. Sure I had him.
When we are on the side of what the vast majority of the American people believe in. That is how we won the midterm.
Retired?
Larry Smith remembered. There's Andrew. Okay.
Dinner's ready.
Okay.
He's ready if you're hungry. You sleep longer if you want. It's all.
Just bringing you dinner here on a plate.
Linda, I gotta think about what I'm doing here. I don't.
Let's see.
Hi guys, we're going to start in about 3 minutes. Just a reminder to put your name and PG number in the chat box to everyone if you would like credit for attending tonight.
Oh, come on. There he is.
Good. Hey, Fred. Oh, I gotta type in there too.
All right, it's about 6:30. So Kent, if you'd like to share your screen and get us started.
I don't know if you want me to share my screen, but I'll get us started. Welcome to the last meeting before the end of the school year, folks. Thank you for coming. Looks like we have about 46 participants, and I'm sure you'll enjoy this talk tonight. Thank you, Rosanna, for hosting our happy hour and for hosting our speaker and our meeting tonight. As understand, Treasurer Mike and webmasters down in Disneyland somewhere. Folks, please mute your screen, whatever, and that'll make this smoother. If you have any comments, questions, please use the chat, and of course, upload your PG license if sign in for credit. Again, appreciate the efforts of Amy and Mike. Amy for putting out the newsletter announcements and processing all those PDH credit hour certificates and so forth. It's a big help. It's a big job. Also, we're always on the scout for speakers. We're starting to fill up the fall, but we typically have a full slate for next year by now. So twist arms or pull out your old your old slide decks and think of some stories to tell, because that's why we're here. At least that's why I'm here. Where the officers are going to be mulling over how we might be able to return to in-person meetings or partial in-person or modified, whatever. We understand that the Zoom meetings have created a great opportunity for people that don't have to travel, and for me, it's great to not have to lean on somebody to drive out from Pittsburgh or Syracuse and worry about them on the highways and staying overnight and stuff. Anyway, we're still in that mode of we're talking about how we can do it, because our former venue, which we much appreciated the use of their facilities and their kindness in doing that. They no longer are there, so the venue isn't possible. Although, so we're working on that. If anybody has a suggestion, we're looking for them too. Also, at the last meeting, I mentioned elections of officers, although I don't know how we would vote in this. Rosanna, do you know how you'd vote in this? On this thing? Probably there's a raise your hand thing, but
I haven't explored that.
yeah, I don't know.
We could unmute and all yell at each other at the same time.
That might overload the bandwidth. And honestly, the officers haven't talked about. Usually by now we've all discussed. Well, will you do it again next year? Will you do it again next year? But we haven't done that. Anyway, I think until we get voted out, hopefully so far we'll keep doing this because it's enjoyable and rewarding in its own way, so that we can host people like Chuck Cravotta to tell us a story and make us go, wow, this is why I love what I do. This is fascinating stuff. And so really, unless there's something else to discuss, let's get on with it. Chuck, I think this is his second or third time presenting to us while I was president. And I've always been amazed and fascinated because his topics have always been sort of interesting to me and something I've never been able to get much experience in. It was typically involving acid mine drainage and stuff, and the geochemical reactions and so forth. Chuck works for the USGS. He got his BA in environmental sciences from UVA and his master's and PhD in geochemistry and mineralogy from Penn State. He has researched geochemical and hydro processes and sources, transport, attenuation of metals and nutrients. At his last talk, he showed us how a stream up near Minersville was, losing water for a while when it was on top of old deep mines, and then picking that water back up. And I thought it was fascinating. Anyway, he applies scientific and regulatory programs for prevention and remediation of aquatic contamination and mitigation of impacts to human health and welfare. We really appreciate his participation in HAGS, and I'm looking forward to his talk on the Marcellus Shale groundwater quality thing, because really I think a lot of the areas where the shale was being produced personally, again, were areas that I never got to unless except for the Marcellus Shale. And I've lived in Pennsylvania for over 40 years. And a lot of the background hydrogeology and the geochemistry is very sparse up in the Northwest up there. So hopefully we'll see some more about it. So Chuck, are you ready for this?
Yeah, let's see if I can get this started. And I already did something wrong. I need to share my screen first.
Well, it was working on the test drive, so.
Yeah, so you're seeing my desktop now, right?
Yep, nice birds.
Yep. Oh, I have the best birds at my house.
Right.
I live against the Blue Mountain on the I'm not even going to say it right. I won't even try. On the flyway.
Cool.
So.
All right. Well, I'm going to drop off and give you full bandwidth.
Okay. So I want you guys to see the main screen and not my notes. I think this will work.
Yes, we are seeing your slide and not your.
Okay, so thanks for the introduction, Kent. We can get on with it. So shale formations containing economic quantities of oil and natural gas are found in 30 states. And currently the Marcellus Shale play in the Appalachian Basin, which spans parts of Ohio, West Virginia, Pennsylvania, and New York, is the largest source of natural gas from shale in the US. And as you know, the shale gas is produced by fracking, which is also referred to as unconventional production. So oil and gas wells are distributed widely across Pennsylvania, especially in the Erie and Ohio River basins in the west, and the, let's see, so, and then in the Susquehanna Basin in the north central area. Many of the wells are historical conventional wells shown by the black dots. The red dots indicate the unconventional wells drilled mainly since 2008 for extraction of natural gas from Marcellus Shale. So various water resources investigations have taken place to document background characteristics and possible effects of Marcellus gas development on water supplies. From 2011 to 2017, the USGS conducted a series of county-wide studies of groundwater quality used for domestic supplies in 7 counties: Potter, Clinton, Lycoming, Sullivan, and Bradford counties in the north central area where Marcellus gas production has been ongoing. And additional studies were conducted in Wayne and Pike counties in the northeastern area where there's been negligible gas development. So the northeastern area where Wayne and Pike counties is in the Delaware River Basin, and the others are primarily in the Susquehanna Basin, but there's also a little bit of Genesee and Ohio River Basin, but I'll generally refer to the Susquehanna Basin as the western area. So well owners, local communities, conservation groups, consultants, natural resource agencies, and regulatory authorities need information on the chemical characteristics of groundwater to assess the quality of drinking water on human health and potential influences by various land uses and natural conditions, including the geology and hydrology. Before 2011, there were few publicly available data on groundwater quality in the north central and northeast parts of the state where Marcellus gas development had been ongoing since 2008. To fill the data gap, USGS conducted studies in 2011 to 2017 across 7 counties. And each of these was conducted separately. For those studies, private homeowner wells were used for domestic supply, and they were analyzed for water quality. So consistent methods of well selection, sampling, and analysis were used for each of the county studies. An approximate randomized design was used for well selection. Well construction details were verified. Sampling was conducted in a single day at each well using field methods to measure unstable parameters such as the pH, temperature, and dissolved oxygen. And then water samples were collected for laboratory analysis. The untreated groundwater was sampled at the pressure tank or outside spigot using the installed pump. And a typical well was cased into bedrock with an open hole at the bottom. But a few wells were completed in unconsolidated superficial deposits that had screens at the bottom. And at the time of sampling, potential sources of contamination such as bacteria at the well cap and copper or lead plumbing were noted. The sampled well depths across the study area range from 33 to 1,300 feet. Several wells with depths greater than 400 feet were sampled in each county. Groundwater sampling campaigns for each county were conducted during spring through summer in a given year when the water table conditions were generally stable. Field measurements were completed for pH, conductance, temperature, dissolved oxygen, and alkalinity. Laboratory measurements were completed for major cations and anions, trace metals, nutrients, radiochemicals, volatile organic compounds, dissolved gases, including methane and ethane, plus fecal bacteria. The corresponding water quality data and interpretations for each of the county studies were published in separate reports by the USGS, mostly in the scientific investigation series. Today, I'm going to talk about a synthesis of those data presented in a recently published journal article. And that synthesis was actually facilitated and supported by the Pennsylvania Geological Survey. The title of the journal article, which is the title of the talk today, is Factors Affecting Groundwater Quality Used for Domestic Supply in Marcellus Shale region of North Central and Northeast Pennsylvania. I want to acknowledge my co-authors, Lisa Senior and Matt Conlon, and also contributions from John Clune. And this is an open access paper, so it's accessible at the link to anyone that chooses to get it. So this map shows the density of gas wells by the gray shading and the locations of the 472 wells as point symbols. The predominant lithology of the aquifer supplying each well is indicated by different symbols. Red squares indicate sandstone. Star symbols indicate shale. There's triangles and diamonds. So triangles, diamonds indicate siltstone and carbonate. And the open circles indicate unconsolidated superficial deposits. These were mainly in the valleys. About half the water wells were in Delaware County, in Delaware River Basin, in the eastern area where sandstone is the predominant lithology, and where Marcellus gas has not been developed. Other wells were in the Susquehanna, Allegheny, and Genesee Rivers watersheds in the western area, where a variety of lithologies were sampled and natural gas development's been extensive. Thus, an attempt was made to evaluate variations in water quality in relation to the proximity to gas wells and aquifer lithology, plus other variables such as topographic setting. So conceptual hydrogeochemical models presented to explain the common water quality characteristics and hypothetical evolution of water quality along groundwater flow paths. Shallow fractured rocks have experienced greater flushing by meteoric water over geologic time than deeper rocks, which retain greater amounts of residual brine, including sodium and lithium on cation exchange sites in the intermediate zone, and sodium, lithium, chloride, and bromide in the underlying regional system. In recharge areas and in local flow zones, calcium, magnesium, bicarbonate type water, sometimes with sulfate and chloride, is common. These shallower waters tend to have relatively lower pH and higher dissolved oxygen concentrations than groundwater of intermediate and deeper zones. In the intermediate zone, the pH tends to increase while the dissolved oxygen decreases as the groundwater transitions to predominantly sodium bicarbonate type waters, sometimes with lithium and sulfate. Elevated sodium and lithium commonly result from cation exchange reactions where the calcium and magnesium moving down displace the sodium and lithium from the exchange sites. Deeper saline or brackish groundwater that's enriched with sodium and chloride commonly is found at depth and may also be present in discharge areas such as stream valleys. Methane commonly occurs in groundwater. If you look for it, you may find it. Typically, it's in groundwater that has low dissolved oxygen. The methane may be derived by microbial processes and or thermogenic processes. This slide shows the cumulative frequency distributions or probability plots of selected major and trace inorganic constituents of the 472 samples. Dashed horizontal lines indicate the highest common reporting limit for a constituent. Because different reporting levels may have been used for the counties, values reported below this level were set to this common value. The groundwater samples exhibited wide ranges in pH from 4.5 to 9.3 and wide ranges in concentrations of alkalinity, sodium, chloride, bromide, lithium, and methane, all of which may be associated with brines or gas well water, flowback water, but are commonly occurring across the area. Primarily on the basis of dissolved oxygen, which ranged from non-detect to 11.5 milligrams per liter, the samples were classified as oxic, anoxic, or mixed. The redox state and pH are key variables to understand the subsurface environment and potential for element mobility in this aquifer. So a total of 28 bedrock units has been mapped within the study area. Unconsolidated superficial deposits locally as thick as 300 feet overlie the bedrock in major stream valleys. All the mapped bedrock and superficial units supply potable groundwater within the region. However, the Upper Devonian Catskill and the Lock Haven formations are the most widely distributed and hence most used for domestic drinking water within the study area. The Middle Devonian Marcellus Shale lies more than 4,000 feet below these fractured rock aquifers in much of the study area, but it occurs closer to the land surface in the eastern part of the area, cropping out along the Delaware River in Pike County. The bedrock units and superficial units, although there's a lot of variability within each unit, we generalize the lithologies using the predominant lithologies into 5 general classes. So carbonate, shale, siltstone, sandstone, or unconsolidated, based on the primary lithologies. Of the 472 sampled wells, 69% were completed in sandstone, 19% in shale, and the rest were in the siltstone, carbonate, and unconsolidated. Most of the groundwater were classified as sandstone from the Catskill Formation, there were 286 samples, so about half the samples. And most of the shale groundwaters were from the Lock Haven. Only 2 samples were from the Marcellus Shale, which were grouped with other samples from shale bedrock. The major bedrock lithologies are not equally distributed across the area. So this is a generalized geologic map showing the major lithologies. And it also shows the well point symbols with the lithology indicated. And sandstone is the predominant lithology, especially in the Delaware Basin and eastern area, where shale is abundant in the Susquehanna Basin, especially in the north central area. So groundwater quality could be influenced by these spatial variations. The pH ranged widely from 4.5 to 9.3, with the highest medians for shale and carbonate, but it was most variable for the sandstone. So the highest and some of the highest and lowest values were in sandstone. Alkalinities were also greatest for carbonate and shale because of the calcareous minerals associated with these units. And total dissolved solids were greatest for shale and carbonate aquifers, reflecting the alkalinity, which was the major component of dissolved solids in these units and most others. So this map shows the density of gas wells on the base. And in this case, the concentrations of chloride for the point symbols. The chloride concentrations ranged over 5 orders of magnitude and could be related to a combination of factors, including influence from deep brine, road de-icing salt, and other sources. So, most of these homeowner wells are along roads, and roads are typically in valleys. So there should be a combination of road de-icing salt and brine influencing these waters. Later, I'll explain how chloride and bromide concentrations may be used to distinguish between the two main sources of salinity. Sodium and lithium concentrations were elevated compared to the chloride from brine or road salt sources. So we actually have excess of these cations, indicating possible influence of mineral dissolution and cation exchange processes. The sodium-enriched waters, which were mostly from shale and siltstone aquifers, had the greatest frequency of elevated lithium, as well as elevated pH, bromide, and methane. So generally, the highest values for lithium and sodium were observed in these silicicrastic rocks, where minerals such as illite and chlorite that are involved in cation exchange reactions are relatively abundant. Methane concentrations ranged over 5 orders of magnitude and were not correlated with the proximity of gas wells or density within 1 kilometer of sampled wells. Although some of the highest methane concentrations were observed in areas where gas development was active, other samples having elevated methane were also observed in areas outside of gas development. Lithology explains most of the variability in water quality across the region. So these, the two most abundant rock types, sandstone and shale, are shown side by side in the upper set of box plots. The median for a given group is shown as a horizontal line, and notches on either side of the median indicate the 95% confidence interval for that this median represents a large population. And if the medians overlap, if the notches overlap, the medians are not significantly different between the adjacent box plots. But if the notches do not overlap, the medians are different. So for example, groundwater from sandstone had lower medians for methane, lithium, dissolved solids, pH, and alkalinity compared to the medians for shale. And yet the medians for chloride were equivalent for the two units. And the lower set of box plots now shows data for only one lithology. That's the sandstone of the Catskill Formation. So now we've got one lithology, but we're dividing it by river basin. So the left, we have the Susquehanna Basin, and the right, we have the Delaware Basin. In general, chloride, lithium, dissolved solids, pH, and alkalinity were not significantly different between the two river basins. However, methane was greater in the Susquehanna Basin compared to the Delaware Basin. Nevertheless, the samples having a concentrations of methane greater than 1 milligram per liter, there was a similar frequency of occurrence of those samples. And generally, decreasing concentrations of gas from west to east correspond to increasing thermal maturity of the rocks from west to east. So this really isn't a surprising finding. So these charts show constituent concentrations as a function of the pH for this 472 samples with symbols indicating the aquifer lithology. Now, if the correlation is significant between the constituent and the pH, the Spearman correlation coefficient is shown. And if it's insignificant, there's no value indicated. For example, lithium and sodium are positively correlated with pH, but chloride and bromide are not. Methane is weakly correlated with pH. Oxygen is inversely correlated. And the decreasing oxygen concentration with pH could reflect compositional changes along a groundwater flow path. And the interesting that the hardness peaks around neutral pH, and then it decreases as we get to higher pH values. The decreasing hardness or water softening results from cation exchange, or where the calcium and magnesium are removed from solution while sodium and lithium are liberated from clay minerals. The alkalinity increases to about neutral pH, after which it increases, if at all, it's modest. And equilibrium with calcite maintains the relatively constant high values of alkalinity at the neutral to alkaline pH values. Excuse me. So intercorrelations among the measured variables are indicated by this principal components analysis model. And that was based on 25 constituents, and significant correlations among the PCs and variables that were excluded from the model are shown below the primary model. So there's 5 principal components that explain the 71% of the variability in the data set. The PCs are interpreted to represent geochemical processes as follows. So PC1's exchange sorption with pH and lithium as the primary loadings. PC2 is reduction oxidation with manganese and iron positively loaded and negative loadings by oxygen and nitrate. PC3 is hardness with calcium and magnesium. PC4 is salinity with chloride and bromide. And then PC5 is barium and potassium. Methane is loaded on multiple PCs, so indicating that the observed variability of methane may be attributed to several environmental factors, such as the geochemical evolution along flow paths, redox conditions, or possibly mixing with saline water. The PC scores differed among the 5 lithologies, reflecting variations in the prevalence of specific geochemical processes in the primary aquifers. And likewise, so that's this I'm really not going to get into it, but you can see, for example, this PC1 is the highest frequency of high scores are associated with the shale and siltstone. And and then the hardness, which was PC3, is primarily in the carbonate and shale, just for example. And likewise, differences in the pH or redox classes reflect the importance of these geochemical master variables on mobilization of specific constituents. So again, PC1 was the one that had pH as the primary loading, and of the redox one was this right here. So you can just see the example where when we use the classifications, we get a similar result with the principal components analysis model. Now I'm going to spend a little time explaining some geochemical models because they're broadly applicable. You've probably seen these types of curves before. These are conservative mixing curves showing that are the result of mixing fresh water with increasing amounts of eastern oil and gas brine having the composition of Appalachian Basin brine. So that's the upper curve. And then the lower curve is mixing with road salt or halite that has very low concentrations of bromide. So along the brine mixing curve are data points for salt spring, which is a naturally occurring discharge of saline water in the study area. Many of the groundwater samples, such as these with high chloride, BR913 and LY735, follow along this brine mixing curve, as do many other samples that have high lithium concentrations. And so these samples generally have high lithium and methane. Other samples with relatively low bromide plot along the de-icing salt curve. So for example, LY722, which is actually the sample that had the second highest chloride of all the samples in our data set, plots along the road salt mixing curve. And it actually has high lithium. Road salt doesn't have high lithium, but the sodium from road salt could displace lithium from mineral surfaces. Now the graph on the upper right shows the chloride to bromide ratio to chloride. So it's the same data, but expressed differently. And now with methane indicating for the data points. And in general, those samples with the high methane tend to occur along the brine mixing curve, but there are also samples with high methane on this de-icing salt curve, including this sample LY722. Now the lower two graphs show sodium versus chloride and lithium versus chloride. Again, now with lithium as the symbols. And what we see here is instead of samples falling along the conservative mixing curve, many of the samples that have high sodium and happen to also have high lithium are off the curve, which implies these have excess of these cations. And we can explain that excess as a result of cation exchange. And those same samples also tend to have high pH. So the excess sodium and lithium combined with high pH are interpreted as evidence of aquifer mineral dissolution combined with cation exchange examined with geochemical models. So you've all seen Piper diagrams. And here what I'm doing is I'm combining just displays of data points with the curves for the results of geochemical forward reaction models. So first of all, the data points are displayed again using the primary lithology symbols. And you can see, for example, the sandstone, the red squares plot all over the place. On top of the data points, well, and also then over here on the left corner is primarily the carbonate rocks. In fact, I left some of them off just so we could see that there were other rock types that had these calcium bicarbonate type waters. But on top of the data points are curves showing the results of geochemical models that may be interpreted to indicate potential water quality evolution along groundwater flow paths. So all the models consider mineral dissolution and cation exchange and mixing with saline water. So we start with the evaporation of rainwater and mix in a little bit of minerals to come up with something like a recharge water. And at this break point, I mixed road salt with the water. So basically a shallow groundwater mixing with road salt, and it moves right across the diagram like so. The other models do not add salt, but instead as the final step, they add brine. It's a very small amount of brine, up to 0.7% at the end of the arrow points. So the red curve and the blue and the green have the same quantities of minerals involved in reactions. The only difference is the blue and green curves involve cation exchange, the red does not. So we get over to this corner with the calcium bicarbonate waters, and then those that involve cation exchange continue to evolve down here to this sodium bicarbonate type. And then with the mixing of brine, they end up in the chloride zone. Okay, so the diagram on the upper right shows the samples with the highest pH values, the blue dots, correspond with the more evolved sodium bicarbonate type waters. And those that have the near neutral pH correspond with the calcium bicarbonate type waters. And on the lower left, we can see that the samples that have the highest lithium correspond with the more evolved waters that underwent cation exchange. Whereas methane, some of the samples kind of, high values plot in these evolved waters with the evolved waters, but there are also some samples scattered about that have methane that's elevated, and they're not necessarily very evolved. So the origin of the methane is a little more complicated than perhaps the major ions. These plots show further these geochemical models to illustrate the points that, first of all, these data points are now illustrated by the major river basins. So the brown symbols are the Susquehanna and the blue are the Delaware. And for the most part, they overlap. There's not any real distinction by river basin. So the same kind of characteristics apply across both basins. And all these graphs are shown as a function of pH. And you can see how the pH can evolve very differently depending on which of these models is at play. And it's kind of interesting too that, things like lithium and sodium that may be attributed to brine, and they do increase with the mixing of the brine, but we also see a slight decrease in the pH as that occurs, which was not obvious in those Piper diagrams. And then the geochemical modeling results are further illustrated on these bivariate plots, where the lithium is on the y-axis or chloride is on the x-axis. And the point of showing this is that we've got a bunch of trace elements as well, barium, strontium, and bromide. All these constituents, by and large, can be explained by these same models. Now, this is the last diagram. So these two charts show the stable isotope composition. So the carbon-13 composition of methane and the deuterium composition of methane. Both of these charts have carbon-13 on the x-axis. But the top one's the one I want to emphasize. It shows the carbon-13 versus the ratio of the methane to higher chain hydrocarbons. It's a ratio. And so the idea here is that microbial gas tends to be almost pure methane. It's very high methane content and low concentrations of ethane and higher chain hydrocarbons. It also tends to be relatively depleted in the carbon isotopes. So it's plotting up here in the left corner. Whereas the thermogenic gas, these are actually Marcellus gas samples that are plotted on the other the other corner. Now, the way people typically illustrate and explain these patterns across this diagram is a mixing process between thermogenic and microbial gas. Well, the red curves are the conservative mixing curves that would be applicable to the simple mixing. And a few of the samples plot right along these curves. So, and these samples have anywhere from 20 to 50% thermogenic gas. There are some other samples, though, the majority of the samples do not plot along these conservative mixing curves. Rather, to explain these, it would be suggested that the gas composition has evolved as the gas migrates. So the higher chain hydrocarbons, the C2 plus hydrocarbons, degrade. And as they degrade, we shift the ratio. But the carbon-13 composition is remaining the same. And so what we now have is another set of mixing curves with this degraded thermogenic gas mixing with microbial gas, and that explains most of the samples that we measured. And by the way, we only sampled, of the 472 samples, we only analyzed 39 samples for isotopes, and they're all plotted here. But for the most part, then we can explain samples. A lot of these samples have between 30 and 90% thermogenic methane. And again, the symbols represent the higher the concentrations of methane. So the higher concentration samples tended to have more of a thermogenic signature. The lower graph is not as easy to explain. It's often just used without these mixing curves, just to show that there's this potential evolution along this path for the maturation or oxidation. And then this would then be the corresponding result mixing with microbial gas for those same samples that evolve. So in summary, untreated groundwater sampled by USGS during 2011 to 2017 from 472 domestic wells across Northeast and North Central Pennsylvania exhibited wide ranges in chemical quality. The groundwater quality in the eastern part of the study area, where Marcellus gas has not been developed, was similar to that in the western part, where gas development for Marcellus Shale has been ongoing since 2008. Natural variations in aquifer lithology combined with water quality evolution along flow paths generally account for the observed water quality. Sodium-enriched waters, which were mostly from shale and siltstone aquifers, had the greatest frequency of elevated pH and elevated concentrations of dissolved solids, bromide, methane, and lithium. And the geochemical models indicate these ionic characteristics could result from progressive mineral dissolution combined with cation exchange, plus mixing with locally important salinity sources, including Appalachian Basin brine and or road de-icing salt. And isotopic data indicate groundwater methane could be derived from microbial gas mixed with naturally occurring thermogenic gas of deeper origin that may have undergone degradation and possibly fractionation during migration. So that's it, and I'd be glad to answer any questions. Appreciate your attention.
All right, thank you very much, Chuck. If people want to write some questions in the chat box, we can relay them to our speaker. While people are thinking or typing, I wanted to ask the question, why did you skip Tioga County?
That's a good question. We actually attempted to do studies across the entire region, but each of the studies, so the USGS put up part of the money in each case. We have to match our funding with from local sources, state or a local taxing authority. So in cases like Tioga County, and there wasn't necessarily a good reception on the part of the local authorities. Some of the supervisors or whoever, whatever the people are involved, didn't necessarily want to have this work done. In other counties, there were, and I'm not saying that as a whole that was the case, but there were some people who weren't interested, who had some role in making the decision. And then in other counties, there were, we were able to develop that cooperative work. And so the other reason, part of it is just we could only do so much at a given time. So typically there were only 2 instances where we worked in 2 counties in the same year. Most of these were done in different years.
Okay, great, thank you. Alexander asks, is there data documenting any consistent changes in water chemistry between wells located in valleys versus wells located in higher land areas?
That's a good question. So we did attempt to follow a procedure that was published and showed a relation between, it's called the topographic position index. And we tried that and didn't find any significant relations in the data set that we had. I don't want to say, too much about it, but I think that in certain areas that can have a very strong influence, because as you saw in my conceptual model, I was proposing that brine might discharge in valleys. So you might anticipate that there would be an effect that could be observed across the topography, but we didn't see it.
Kent asks, was temperature part of the analysis as differentiation of shallow, intermittent, or deep groundwater?
I have the temperature data. I didn't try to resolve it that way. And that's a good question. I do think there were, as I recall, because I ran these geochemical calculations, temperatures part of that. I did look at the range, and there were some higher temperatures for the real deep waters. So it would be worth exploring further. I haven't done it.
Okay. George asks, are there any cases that you saw that clearly indicate contamination due to gas wells?
There was one particular example where, in addition to the constituents that I reported here, and it's discussed in one of the county reports, I don't remember if it's Bradford or Clinton County. It's one of those two, where there were some anthropogenic organic compounds. Some of those are on the list of constituents used with drilling, but that was just the one instance. And we did analyze for a wide range of organic compounds, and that would have been the most telling parameters, because of how the other constituents seem to reflect natural variability.
Okay. Tom asks, there is known shallow gas production in the area that predates the Marcellus production. Was the shallower natural gas considered in the analysis?
Yeah, so we didn't try to separate well type. When I was talking about gas well density on those maps, we made a decision to not try to distinguish, for the purposes of this analysis, whether it was a shallow conventional gas well historical or unconventional recent well. So yeah, we do recognize that there are these, especially in the northwestern area, there were a lot of conventional gas wells. There's also gas storage fields. So some of the shallower gas has been depleted, and the same formations are used for storage now. So during the summer, gas can be it's been piped up from the Gulf and then put into these gas fields. There's areas in Tioga and in Potter County in particular, and then it's pumped back out during the winter to supply when the demand is high. But at any rate, there's drilling all over the place, and from what we could analyze, with one exception, there was not any real statistical relation between the gas well density or locations and the water quality.
Okay. Kent makes the observation. He says personal observations indicated sampling methods, i.e. extended purge, influenced the results. We thought over purging caused upconing of deep brine, rich water. The temperature was the tip off. So he's just sharing that observation there.
I suppose that might be possible, but these are domestic wells that are used with daily, and I don't believe the sort of pumping we did in preparation of sampling was anything extreme compared to what might be conducted, when they're using the water. So I don't know that that would be something maybe a monitoring well, that would be a situation that you might observe where, the relatively static condition, and then you stress it. But these are pretty much stressed all the time.
So Charlie asks, how many of the 39 samples analyzed for carbon isotopes were classified as biogenic methane? And of the biogenic samples, what was the depth of the well? And were they mainly from bedrock wells or unconsolidated wells?
I can't answer your questions with the information I have in front of me. I'd have to refer to the reports. And I do have an Excel file that has these things in it, but I don't have it right to answer your question, Charlie. Okay. So questions were the depth, and what were the other points? How much was microbial? See, there weren't very many that would be classified as microbial in the extreme. Most were mixed. That was the interesting part. You really couldn't bin, and then most were not binned in the thermogenic bin. There's this one here. Depends on what parameters you want to use. But it was this lack of sort of fitting the end member characteristics is why I developed this sort of a mixing model to try to explain what was actually observed.
Would a peat layer fall in that microbial?
Yeah, I think so. I don't want to pretend I'm an expert on this. I'm not. Pretty much any peat, swamp, they call it, some of this they call swamp gas. And so there's two modes by which the methane's generated from microbial. It's like there's CO2 reduction, and then there's something else, or acetate, I guess. So those processes are the microbial processes. But I don't want to say more because I'm just going to let you know how much I don't know.
Okay, Kent asks, do you think any of the coal fields influenced your results?
Yeah, there's a little bit of indication of that. Up in Potter County, there were some wells that had higher sulfate and lower pH, but these were not a frequent occurrence. It was like 2 or 3 samples out of our data set. And it's possible, I don't have a handy map, but I showed the conventional gas wells and the unconventional gas wells on the same GIS map. I show methane, coal bed methane. Most of the coal bed methane that's of commercial value is from southwestern Pennsylvania, but there's methane that comes from coal degradation, anywhere there's coal, especially if it's got water flooding it, so the methane then develops and stays in place.
Rebecca asks, what percentage of the wells sampled were within a 1/4 mile of drilling activities?
We use 1 kilometer, and I don't know that answer.
But if we read all the reports, we'll know the answer.
Maybe. I'll tell you honestly that I'm not a GIS person, and that was, I have 2 co-authors, so I was relying on Matt Conlon to develop the spatial variables that then I used in the statistical analyses. But for the most part, those things weren't resolved to that degree. It's possible, and the data are available. So there's a data release that goes with this. I didn't mention that. There's a data release. I'd have to find the link for it. It's referenced in the paper, but all the data are available, including the site IDs, which are Latlon style. They're not that precise that you could say what house is what, but I think the site IDs are there. We have to be careful about disclosing locations of water supplies anymore. But no, if people are interested in trying to make use of this data, it's available. And you potentially could answer other questions.
If you want to go back to your title slide, I think it has your email address on it.
Yes.
And then people can write that down and connect with you to get the data or the reports, or if they have anything that we didn't really get addressed tonight.
Yeah, there's a big supplemental information file that goes with this report too. I can provide any of this on request. And I would encourage you to look at the report there's a lot of references. Let me see if I can just escape out of this. Looks like I can't. Let's see, escape. I don't want to do this the wrong way. End show. Okay, so I'm going to open up the paper and I'll give you the reference right off the bat. Not sure how to hide stuff, but I can't scroll with this thing on here, I can do this. Okay. So the data release is available through USGS, and then the article itself is applied geochemistry, but I can provide that if people don't want to click the link and download it. But this is the data release right here. So, I mean, they're kind of odd the way they are presented. I think there's like a little miniature map. Yeah. So right off the bat, I'm not going to be able to tell you what's in it. But there's basically data files. And you should be able to use that and it's all the data that I have in this report. And then there's additional data in the county studies that we didn't compile for this synthesis. Mainly it would be some of these organic parameters, which for the most part were non-detect.
Okay, so we can go to the USGS data clearinghouse and access that. People can email you.
Yeah, we also have there's our web page for the Pennsylvania Water Science Center. There's links for this project, and those links also point to the paper and the data release. And I believe there's county studies. There's you know, I'm going to display my ignorance, but if I don't want to accidentally see Pennsylvania Water Science Center. Let's see what happens. But right off the bat, this is a pretty nice web page. They've worked on it a lot. I haven't really done much, but under science, I think. Yeah, so and maybe shale gas. Yeah, so this is a general overview of the sort of projects and why, for example, you know, Tioga is missing, but this is Jeff Chaplin has been involved in our office for the long term developing this program. And he put the information together for this. And then this is the work I just presented, this synthesis effort. But so this is at the Pennsylvania Water Science Center web page. And this is where you could access all the county studies as well.
Well, great. We don't have any other questions in the chat, and it's about 7:30, so time for you to get a beer. And
Yeah.
thank you very much for your presentation.
Well, I appreciate the interest, and I'll be glad to answer any questions separately.
All right, sounds good. Well, thanks, everybody. We'll look forward to seeing you in the fall at the meetings, and Amy will be sending you emails. Maybe we can get a field trip together for the fall. And have a great night.
Thank you. Look forward to seeing everybody.